Okay, so thank you, Birgit, for accepting to give a talk at our seminar. So let me introduce Birgit Richter from Universität Hamburg, and she will speak about detecting and describing ramification for structured ring spectra. All yours.
Okay. Thank you for the invitation. So I'm aware that this is not home turf for most of you. So so please feel free to ask questions. Yeah. So I mean, since the mid-90s, we have nice ways of finding geometric representations for cohomology theories, and in a way that you can actually do algebra with them. And then there are questions like, say, Galois descent for K theory, or you have other questions where suddenly the quality of maps plays a crucial role. So what we tried to do was find a good notion of wild and tame ramification for maps of ring spectra. So, but let me just go back to the sort of classical situation that you probably all know. So let's start with finite extensions of the rationals. So if you have an extension of number fields and the corresponding map on rings of integers, then you can talk about ramified primes or prime ideals. So you say that a prime ideal ramifies if you view it as an ideal in the bigger ring, it just splits up in powers of prime ideals, and one of the factors is larger than 1. So you have multiplicity greater than 1. So this looks like a singularity geometrically. And so ramification can be tame or wild, so it can be okay or can be pretty nasty. So you have a residue field just because, I mean, these, you have a prime ideal, non-trivial one, so you can build the residue field, and this is a finite characteristic. And then you say that the ramification is tame if all the indices that you have are relatively prime to the characteristic of the residue field. So, and otherwise, you just call this wild. And my favorite example is sort of probably the easiest one. You take the rationals, you join square root of -1, and then the corresponding extension of rings of integers is just the integers mapping to the Gaussian integers. So an extension that we know from early on, and this looks pretty innocent, but this is actually bad in the sense that the ramification is wild, because 2 is 1 plus I times 1 minus I. So up to a unit, it's 1 plus I squared. So the prime ideal 2 actually is a square of the prime ideal 1 plus I. And 2 happens to be the characteristic of the residue field Z mod 2. So the prime ideal 2 is actually widely ramified. This is a prototypical example. And then there are lots of general statements about ramification. You can only have finitely many bad things, and so on and so forth. But one thing to bear in mind is that the notions are defined in terms of prime ideals and things like that. This is sort of a problem that will hit us later. Well, not every map of rings or commutative rings is of that nice form. So not everything is just rings of integers. So Auswander and Buchsbaum sort of defined a more general notion for general Noetherian rings. This is pretty involved, so I won't do that. But Auslander then also went on to define Galois extensions for commutative rings in order to understand the completely nice case. So you have Galois extensions of commutative rings, then you have ramification, and then you might wish to distinguish the several types. So if you start with a G-Galois extension of number of fields, then the corresponding extension of number of rings is unramified, if and only if it's what they call a Galois extension of commutative rings. And this has to satisfy two properties. So you have the familiar fixed point condition that the fixed points of the big ring of integers is the small one. But secondly, you have to ensure by hand that this extension is unramified. And this translates to the fact that if you induce your ring up with itself over the smaller one, it just splits into G copies of the ring. So the fixed point, so what the take-home thing from this is to say the fixed point condition is not enough to ensure that this extension is unramified. For instance, in the example we had in the Gaussian integers, the fixed points are fine. You have complex conjugation and the fixed points are the integers, but still you have ramification, and ramification will show up in that second condition. This is not an isomorphism, and to be extremely precise, the map is important. So you just send two elements x tensor y to their product, but first you twist the second variable with a G action. And in the case of the Gaussian integers, then this map is not surjective. You're off by a factor of 2. So if you have a Galois extension of commutative rings, this is unramified, and this second condition is really described by that map. And then you have an analog of Dedekind's lemma. You can do all the things you're used to from classical Galois extensions of fields. So the plan for today is as follows. The first question is, what the heck is ramification for ring spectra? And then what took us quite a while was to say, when are they tame or wild? But the most important thing is examples. We propose a definition, and the only way to test whether this is any good is to deal with examples, and they will be mostly in the vicinity of topological K-theory or topological modular forms. But if you don't know what that is, relax. So how do these examples arise? Well, you probably all have your favorite homology theory, cohomology theory. For instance, just singular cohomology with coefficients in a commutative ring. There you have a nice cup product, which gives you a multiplicative structure. And as the ring is commutative, this is graded commutative on the level of cohomology. Then you probably all have your favorite Bordism theory, say complex Bordism. That's my favorite, but you might prefer string or whatever. And so products of manifolds and use a ring structure on these things. Or you might want to study vector bundles on your space. So you might consider real or complex vector bundles. And then you might want to understand, you have a given finite CW complex, say, and you want to understand what are the different possible vector bundles of finite rank over my space. And you might do this in real and complex flavor, and this gives you the two notions of topological K-theory. So KO for the real version and KU for the complex one. And last but not least, if you like elliptic curves and modular forms, you might wish to take them and cook up a cohomology theory from them. This is actually pretty involved, so I don't want to talk about the construction of this thing. there is something like topological modular forms, which gives rise to cohomology theory. And one version of its string of coefficients has something to do with modular forms, and I'll actually come back to that later. So for K-theory, you have the tensor product of vector bundles. So in the first three examples, coming up with the ring structure is not that hard, or you have a geometric feel for it, or you're used to it from singular cohomology. In the last fourth example, that's less clear, but all these things can be represented by commutative ring spectra, which means that your cohomology theory evaluated on space X is just a Being group or whatever of homotopy classes of maps from your space into this representing object. So, and we usually try to use notation that's similar to the cohomology theory. So you have HR, the Einberg-MacLane spectrum that corresponds to singular cohomology, MU for complex cobordism, KO, KU, and TMF. And of course, there are many more. So this is just a tiny fraction of what's out there. So, and then there's something, so you have these commutative products on your cohomology, and this corresponds to something that just looks like a monoid structure on the representing object. So you have something that's called the smash product. This is very similar to a tensor product. So just think of a tensor product if you don't like that. And you have a unit map, and the unit in this game is the sphere spectrum that represents stable cohomotopy. And you can write that down. They're actually pretty low-tech models for this, but it would take a while to define this. But a commutative ring spectrum for me is just a commutative associative monoid in that sense. So these things were around since the 90s. And then people cared about the actual quality of the ring structure these things have. So in 2008, or even, I mean, this was the published version, so this was around since 2000 maybe, John Rocknes came up with the definition of a Galois extension. And so you have the canonical things you want. So you have a map of commutative ring spectra, so a map of cohomology theories, you have a group action, and then you just do copy and paste from the Galois extensions in commutative rings. So you have the very two same properties, but you replace actual fixed points by homotopy fixed points. So you want that the map from A to the homotopy fixed points is a weak equivalence. And secondly, you have the unramified condition that B smash B over A just splits up into copies of B indexed by the Galois group. And it's the same map. It's, I mean, in spectra, you don't have elements, so you have to define this via an adjunction, but it's really the same map. You act with G on the second component, and then you multiply your elements, and this gives you that map. So a Galois extension has a fixed point condition and an unramified condition. I mean, so everything is made homotopy invariant, so there are some cofrequency conditions that I didn't talk about, and you have homotopy fixed points, but otherwise it's really the same definition. So, and this is consistent with algebra. So if you take singular cohomology with coefficients in number rings, then you get a Galois extension of ring spectra if and only if this was a Galois extension of rings. So you don't lose information if you embed algebra with the help of Einberg-MacLane spectra into topology. That's sort of a sanity check. Nothing goes wrong there. You also don't gain anything, but that's this. But then there are completely different Galois extensions out there. For instance, if you talk about vector bundles, you can complexify a real vector bundle, get a complex one. And so this induces a map of cohomology theories, and it actually induces a map of commutative ring spectra from real K theory to complex K theory. So you have this map. And then, of course, if you have a real vector bundle, then complex conjugation doesn't do anything. So you have a C2 action on Ku given by complex conjugation, and Ko is not sort of touched by that action. So, and then Wagner shows that this is actually a C2 Galois extension. So in particular, it's unramified. And just the word of warning, these Galois extensions are far from behaving nicely on homotopy groups. Of course, if you have Eisenberg-MacLane spectra, the only information you have is the homotopy groups. But in this example, for instance, if you take the corresponding homotopy groups of your representing spectrum, the extension is ghastly. I mean, the homotopy groups of Ko, you have eta in degree 1, which is 2 torsion and it's nilpotent. You have a generator Y in degree 4. And then you have the bot periodicity element that are called omega here of degree 8. And you have relations in this ring. And this maps to Ku, where the coefficients are just Laurent polynomials in a variable of degree 2. So everything is clean there, no torsion, no nilpotency. So as a map of graded commutative rings, this is as bad as it gets. So you do not detect Galois extensions by looking at the homotopy groups, which is bad if you think about the algebra where you just looked at prime ideals. And so this is one indicator that this won't work here, at least not if you take algebraic ideals. So let me just drop some other examples. If you take complex K theory at an odd prime, it just falls apart into pieces. And there's just an idempotent, and you can split off a bottom summand. And if you P complete, this is actually a CP-1 Galois extension. That's an important but sort of synthetic example. And then there are important examples around TMF. So I saw that Emma is there, so you might like this. So what are these things? So TMF 1.3 is, think of elliptic curves, and you choose a point on that curve that has exact order n. So in this case, n is 3, so you choose a point of exact order 3. So if you think about a torus, then, well, you just take 1/3 of the torus length and you just have a point of exact order 3. This would be over the complex numbers, but this is defined over general rings or even over schemes. So, but this is maybe the picture you should have in mind. And TMF 0.3 just says, I don't care about the point, I just care about the group it generates. So you fix a group, a cyclic group of order 3 in your elliptic curve. And then you have an action. You have one point of order 3. It squares another point of order 3. So you have a C2 action on the points of order 3. And so this is a C2 Galois extension. And you can do the same thing with level n structures. So roughly speaking, you choose a map from Z mod n times Z mod n into the end torsion points of your elliptic curve that has some very nice properties. And then you get a GL2 Z mod n Galois extension. These are sort of examples that people care about. So all these things are unramified, except for the second example. Believe me, you don't want to look at the homotopy groups. You don't want to see that. That's really not nice. So in particular, all these things were Galois extensions, so they were unramified. And if you have an extension that's unramified, it's separable. And then you get that the topological version of Hochschild homology is as small as it can be. It just gives you back the ground ring. So the map from the extension to relative Hochschild homology of B over A as an equivalence. And you also get that a topological version of Andre-Quillen homology vanishes. So, so these are just topological versions of Hochschild homology and Andre-Quillen homology that try to measure the same things that you try to measure with the algebraic counterparts. So what you know is if one of these things goes wrong, so if THH is bigger than just the base ring, or if you actually have non-trivial homotopy groups of Andre-Quillen, so a non-trivial Andre-Quillen homology groups, then there has to be ramification. So this is a method of detecting ramification, and THH is not so bad to calculate in many cases. This can be done. So, and this actually ties back nicely to the case of number rings. If you have an extension of number rings, then the zeroth homotopy group of topological Andre-Quillen homology of this ghastly thing is just the usual Kähler differentials that you know and love. So you just measure the Kähler differentials of the bigger ring of integers with respect to the smaller one. And for instance, the annihilator of the Kähler differentials is the different, and the different tells you about ramification. So this might not be a bad spot to look for information about ramification. So how do we get trouble? I mean, we want to understand ramification. So far, I told you about the unramified case. So where are ramified extensions? So the result by Matthew was sort of expected, but he proved it in 2016. If you have ring spectra with no negative homotopy groups, so these are called connective, then things that you saw in the example of K-theory can't happen. Then the induced map on homotopy groups has to be nice. So we saw KO to KO has nilpotency, additive torsion, you map it to something nice. So this will never ever be étale. So if you cut away the negative homotopy groups, this is far from being étale. So étale, just think of being very, very nice, better than smooth. So that would happen. So this is actually a pretty good method for creating trouble. So the recipe is take a Galois extension, cut away the negative homotopy groups. You can do that in a civilized manner, and you will be sure to get into trouble. So that's what we will do. So we cut away negative homotopy groups and look for examples. If you know a bit about homotopy theory, then you might say, well, this is just cutting away negative homotopy groups is not a good idea. Yeah, you have to be a bit careful, but this is the rough idea. So what is the issue if we want to understand ramification? There's one major difference between algebra and brave new algebra, namely that we don't really have a good notion of ideals. I mean, there was a definition proposed by Jeff Smith that was aimed at associative ring spectra, and it has certain features that, for instance, Markov exploited to some extent. But this is really geared towards a notion of two-sided ideas in the associative context, and it doesn't really work if you plug in commutative rings. So we don't have ideals. So the whole notion of saying, I take a prime ideal and I look what happens, doesn't really work. That's one big bug that we had to work around. Then what you like to do in algebra, before you start thinking, you just calculate the module of Kähler differentials, because this is usually easy. You can see torsion, you can see some relations, and that's the first thing to do. If you do this with topological and equivalent homology, and you don't happen to have a Thom spectrum in your hand, then you're usually doomed. I mean, this is, there are no good methods of really calculating that unless it's a Thom spectrum. So this is the second problem. And then the last one is, well, we like to think of periodic ring spectra as being sort of analog of really fields or number fields. And then sort of cutting away the negative homotopy groups could be an analog of rings of integers. You have an invertible element, a periodicity generator, you cut it away, you just keep it as a polynomial generator. So this looks similar. So what is this game? So we usually use small letters for the connective covers. So you just cut away the negative homotopy groups and you get an isomorphism in all degrees greater or equal to 0. But this might not be a good idea. For instance, if you have a periodicity, it might just take elements in positive degree, drag it back down into lower degrees with the inverse of the periodicity element, but you still are in positive degrees. So, but you have a negative power of your periodicity element in there somewhere. So you might create junk that you probably want to cut away, but not with just sort of sawing it off. And then there's other problems, like for instance, topological modular forms were invented to have good connections to modular forms, to have nice genera. And there are several examples where if you just cut away the negative homotopy groups, you really get bad stuff. So if you take an element of exact order n on an elliptic curve, produce a ring spectrum out of this, you get capital TMF1, and then you usually pass to the compactification of the corresponding moduli space to allow for nodal singularities. If you then take the connective cover, this has a non-trivial pi1 in certain cases, and this does not correspond to any modular form. So there is just junk in there that shouldn't be there. So these are the main issues that we are facing. There are other ones, but yeah, this is sort of bad enough, right? So let's start with topological and recurrent homology. So if the homotopy type is out of reach, what can you do? Well, we saw in algebra that the bottom homotopy group actually contained the information of the Kähler differentials. So maybe the bottom homotopy group can tell us something. Maria Bastera proved a Horevich theorem saying if you have connective spectra, so no negative homotopy groups, you have an equivalence on homotopy groups up to some stage, then topological and recurrent homology also all starts at one stage higher up. And you can actually calculate the bottom homotopy group just by calculating the homotopy group of the co-fiber. So you can always, well, it's not completely dumb to do that, but it's not hard to calculate the bottom homotopy group of TiQ. So our first hope was, well, this might tell us something about the quality of ramification. But then you start to calculate. So you take complex K theory, localize it and up prime, it falls apart. You take the bottom piece, map it in. You know it has to be ramified. And then the bottom homotopy group is just a copy of the P locals. Okay. So this looks nice. What happens if you do the same thing with real K theory mapping to complex K theory on the connective covers? You get a copy of the integers. So you could also localize, and then it would just look the same. So there's no real distinction. So in particular, you don't see a difference in the type of ramification. And then you can play that game for other examples, connective covers of points of order 3 of an elliptic curves and so on, or just another extension in the vicinity of topological modular forms, and they all look the same. So that was a bad idea. We knew that there was ramification. This sort of says, yes, there is ramification, but it doesn't tell us anything more. It, in particular, doesn't tell us whether it's tame or wild or anything. So that was dumb. But on the other hand, I mean, this might come handy. I probably should mention that John Rocknes has some higher homotopy calculations of some of these TiQ groups where you actually see some torsion, but it's not so clear whether this is actually detecting ramification. So this didn't work. We also calculated several relative THH groups, or actually the complete homotopy groups of relative THH. So you can do this, but the answer is the same. This all just detects ramification, but it doesn't really tell you what's going on. So the problem is, if you try to copy from algebra, you have to sort of dig a bit into the things that people usually don't use. Because prime ideas work so fine in number theory, yeah, why not use them? So we were looking for other criteria that tell us about tame and wild ramification. So and then there is a so Cassels-Fröhlich, as usual, is actually pretty helpful there. So there are two classical results that actually are amenable to be transferred into stable homotopy theory. So if you have an extension of number rings, or more generally a nice extension of Dedekind domains, then the ramification is tame if and only if the trace map is surjective. So the trace just takes an element and it just applies all elements in your Galois group, and you take the sum of them. This is invariant, so it ends up in the base ring A. So, and if this map is surjective, then the ramification is tame. Well, surjectivity is also a bad notion for homotopy, but this leads to something that we actually can transfer. So, and for number rings, you can actually show that the extension is tamely ramified if and only if the norm map or the trace map is surjective. There's this weird confusion of notation. So that's in Galois theory, you usually call the norm the product of things. But in sort of the context of tape cohomology and these things, you usually call it the norm. So it's just the same map. You take an element, you apply every element in the Galois group, and you sum things up. And now we can sort of move on to homology, the norm factors over the co-invariants. So it maps from the co-invariants to the invariants. So it induces a map from the zeroth homology of the group, Galois group with coefficients in the extension, to the zeroth cohomology of the group with coefficients in the extension. And you can measure whether the norm of the trace is nice by building Tate cohomology. So you can measure the deviation from the trace map or the norm being an iso or surjective before you took in coinvariance by defining Tate cohomology. And there is actually a homotopy theoretic version of this. You have an analog of the norm map going from the homotopy orbits to the homotopy fixed points. That's the norm map. And then the Tate construction is just the cofiber of that map. So B lower HG is just the homotopy invariant notion of the orbits. B upper HG is just the homotopy fixed points. So you just make everything homotopy invariant, you still get a norm map, and you study the cofiber. And then classically, you can actually use this as a criterion for time ramification. So in the context above, rings of integers embedded in an actual Galois extension of number fields, then this extension is tamely ramified if and only if the corresponding Tate construction has trivial homotopy groups. This is related to a criterion of Noether. She proved that time ramification is equivalent of having a normal basis, and things with normal basis have Tate vanishing. And this is really connected to Tate cohomology because there's a spectral sequence, has as inputs the actual algebraic Tate cohomology groups with coefficients in just the homotopy groups of your spectrum. And this converges sometimes to the homotopy groups of the Tate construction. Tate construction, Tate cohomology is Z-graded. If your spectrum is also Z-graded in homotopy, this gives you a full plane spectral sequence, so there might be issues of convergence, but in the cases that we study, this actually converges. And then the spectral sequence, if you just have a ring and you transport this into stable homotopy, this just collapses and you just have one line. So this just gives you Tate cohomology back in the algebraic case. So this is what we try to transfer to homotopy theory. So we want to use the Tate construction for saying an extension of ring spectra is tamely or widely ramified. Why is there a chance that this is actually making any sense? If you have a nice map of commutative ring spectra with a group action on the bigger one, and if your extension is unramified, I just wrote it differently, so the thing on the right is just the product of G copies of B, then the Tate construction actually vanishes. John Rockner stated this lemma assuming that A is equivalent to the homotopy fixed points, but you don't actually need that in the proof. But beware, there are assumptions in that lemma that say dualizable and faithful. Dualizable is a finiteness condition, but faithful says if you take an A module, you induce it up to B and it's trivial, then it was trivial before. So B doesn't kill things that weren't dead. And this is unfortunately not for free. In algebra, it is actually for free. If you have an unramified extension, it's automatically faithful. You can't really go wrong. But in algebra, this is fine, but in topology, there are actually Galois extensions that are not faithful as modules. So it's pretty bad. So this is why one has to demand that the extension is faithful. It doesn't come for free. So there's another problem here. If you take a spectrum that only has non-negative homotopy groups and you study its homotopy fixed points, then you often have some negative homotopy groups that are just there and that don't look right. So even, for instance, in the geometric case of topological K-theory, KO is not little ko, is not equivalent to the homotopy fixed points of KU. You have to cut away some junk in negative homotopy groups. So you have to cut away the negative homotopy groups, and then you get the homotopy fixed points. And one can actually show that the negative part of the homotopy fixed points corresponds to the negative part of the Tate construction. So if you leave that in, this will never ever be Tate trivial. So just a warning, you always have to cut away at least the negative part of the homotopy groups of the fixed points. So with all this preparation, what we propose is the following definition. So we have a map of commutative ring spectra. Yeah, we have a G action on the bigger one, so on B. And we assume that B doesn't kill anything that wasn't dead, and that it is finite in the sense of being dualizable. Then if A is equivalent to the homotopy fixed point or the corrected homotopy fixed points in the connective case, then we call A to be tamely ramified if the Tate construction is trivial, and otherwise we call this widely ramified. So this is just a proposition, and in the remainder, I just want to justify that definition. It fits with the examples that we have so far, but this doesn't rule out that maybe in a year or so somebody comes along with an example that sort of doesn't fit, but so far it looks good. So why is this reasonable? If you have a free G spectrum in the sense that you just have G, say tensor something, then Tate vanishes. It also vanishes if you build the thick subcategory generated by such things. So in particular, if you have a normal basis, which is Noether's criterion for tame ramification, then the Tate construction is trivial. So normal basis ensures Tate vanishing, which is sort of in tune with one of the algebraic criteria. So that's sort of a sanity check that might say, well, maybe this is not such a bad idea to take this definition. So, but now the real test starts when you have examples where you have a feeling whether they should be tame or wild, and you just test this definition. So the first test case would be, well, we had that mapping real vector bundles to complex ones and having the complex conjugation action gives you a C2 Galois extension. Then we took connective covers, which still has a C2 action. So what happens there? And this is an old calculation. I actually I mean, I learned this from John Rockness, but I'm not sure who actually did this first. So if you take the take construction there, you get a bunch of Z mod 2s, and this is periodic with period 4. Secondly, if you study elliptic curves with a fixed point or a chosen point of order 3, and you have the C2 action by exchanging exact points of exact order 3, then this is an example where you actually want to do that, to test that. And then the sort of, for us, the ultimate test case was if you study level 2 structures, so a map from ZMod 2, so from the Klein 4 group into the 2 torsion points of your elliptic curve, then on the periodic versions, this was a GL2F2 Galois extension. What happens if we take the corresponding connective cover? What can we say about the take construction there? So in the first case, elliptic curves with an exact with a point of exact order 3, you get as well a bunch of Z mod 2s. Now the periodicity is 8. And in the second case, you get Z mod 3s, and the periodicity is 12. So this is, in both cases, this is a spectral sequence calculation combined with some facts about generalized Einberg-MacLane spectra. There's an old calculation by Mark Mahovald and Charles Resk. They computed the homotopy groups of the periodic versions, where you have elliptic curves with a chosen point of exact order 3, and they just calculated the homotopy groups. So the homotopy fixed points are related to the Tate construction. You can sort of dive into that spectral sequence, look for the connective part, and then actually calculate the homotopy groups of the Tate construction from their calculation. If you have a little bit of help from other people, that, I mean, there's an explanation in a paper by Hill and Meyer that actually say, where are the connective things? And then you can actually see that. Then you see that on homotopy groups, you just get a bunch of Z mod 2s. And we know that these are actually infinity ring spectra. E2 would suffice. And then there's an old theorem by Hopkins and Mahovald that's by now even published by some people, that then says that this is actually a generalized Einberg-MacLane spectrum because 2 is 0 and pi 0. So you just get this result. For the second result, we use a calculation by Vesna Stoyanowska. She proved that the compactified version of level 2 structures on elliptic curve give rise to a vanishing Tate construction. And again, you go to that spectral sequence, you look where the connective part would end up, and then you get the result on homotopy groups. And again, 2 is 0, 3 is 0, and pi 0, and you can deduce the result above. So what is the upshot? Well, we have a Galois extension on periodic topological decay theory, but actually, if you pass the connective covers, you get wide ramification. If you split complex K theory at an odd prime, this gives you a CP-1 Galois extension, and the corresponding extension on connective covers is tamely ramified. Well, here this is just dumb because the group order is invertible. You don't have to do anything here. It just falls off. I mean, the thing we just saw is the C2-Galois extension if you talk about periodic version on the level of so-called compactified things where you allow for nodal singularities. You also get a C2-Galois extension. That's a result by Arkell Matthew and Leonard Meyer. But the Tate construction, as we saw, is on the connective thing is highly non-trivial. But there's a small problem here. We don't know whether this thing is faithful. So this might just be noise. We don't think it's noise, but it doesn't really fit to the definition. So we can't say it's widely ramified. And actually, Leonard proved that this is not dualizable. So it's not finite. It's finite over little TMF, but not finite in this relative part. If we just look at level n structures on the periodic versions, we got a GL2 Galois extension. The Tate construction on the compactified versions is contractible. So the case n equals 2 is the case that Messner showed. The general case goes back then to Matthew and Meyer. But for level 2, our result gives that this is widely ramified. So, and then there are some fun things. So if you like a bit of combinatorics and playing around with Möbius functions and so on, then this might appeal to you. So if we pass to the connective versions of level n structures for elliptic curves, then Leonard actually showed that this is faithful and perfect as a TMF module. So in particular, it's dualizable and faithful. So this makes sense. So what we could show is that the Tate construction vanishes if and only if the group order is a unit in pi naught. And that's actually fun because you can write down what the group order is. Euler function times Euler phi function times some products over some primes and then some explicit given coefficients. And you can write that down. And so if n is bigger than or equal to 2 and 2 does not divide n, or if n is a power of 2, then the Tate construction is actually non-trivial. So taking together this calculation with Leonard Meyer's results then actually says that this is widely ramified in these cases. But for many integers n, the Tate construction is actually trivial because the group order is invertible. So there are infinitely many cases where it's not trivial, so it's widely ramified. And on the other hand, you have infinitely many cases where it is trivial, so it's tamely ramified. So you can just write down some examples. I mean, just looking, when is this bloody group order invertible in pi naught? This is just, sit down and do it. So if n is of the form 2 to the k, 3 to the l, and then this is actually, the Tate construction is trivial. And then you can just write down if you have primes, different primes, product of these, then pi I minus 1 and pi I plus R1 has to be invertible for every prime. For instance, if you take the product of the first primes, that's fine, then the group order is invertible. I always want to make a joke with 42. It works for 42, just calculate it, it works. But for instance, it doesn't work for 66. I mean, pick your favorite number n and just look, it's just a calculation, so you can play around. So it really depends on the prime decomposition of your n, whether this extension is widely or tamely ramified. So let me just close with some other things that we tried and some open questions. There's a classical game that tame ramification of Dedekind domains in knife cases corresponds to log-et-al extensions. So you allow for log singularities. And Stefan Zagave actually showed that the inclusion of the atom summit is log étale. And what we could show is that if you take logarithmic structures, whatever that is, if you don't know it, just ignore it. But if you take this, so if you take the bot elements in KO and KU, they generate a log structure for you. If you take this structure, then KO to KU is not log étale, which fits to the description of being widely ramified. Classically, you would study the discriminant map. So this is adjoint to the trace pairing. So you have two elements in B, and you just act with G, multiply and take the sum over everything. This gives you a discriminant map. And usually this tells you about flavors of ramification, but not here. In the tamely ramified case, you actually get a big co-fiber, a bunch of p-adics. And for KO to KU, this actually looks nicer. So in both cases, it says, yes, there is ramification, but it doesn't tell you anything. So we dumped that. And then the canonical question would be, what about the higher cases where you fix elements of exact order n on an elliptic curve? The next case is n equals 5. Well, n shouldn't be a square. That's usually a bad case. So the next case would be n equals 5. And Behrens-Ormsby actually showed that the take construction on the corresponding periodic things is trivial. But this is, we didn't see a way to push that down to the connective cover. And as I said, it's not even clear what little TMF1n should be, but Leonard Meyer constructs pseudo models of that are actually related to modular forms that have a nice genus. And so there are good models for that, but calculationally, we don't know much about these things. And these things are really, really horrible. So with that joyful remark, let me stop here. Thank you.
Thank you, Birgit. Thanks for the talk. Everyone's clapping. So, questions? Someone wanted to ask a question? Ima, we don't hear you very well. So any other question in the meantime?
I just saw this question in the chat about what is LP. So you just take so if you localize topological complex K theory at a prime, it splits up. And the bottom summand is called L, it's called the atom summand. And then you just P-complete that thing. So on the level of homotopy groups, this has just the p-adics as the ground ring, and then a generator, a Laurent generator n degree 2p minus 2. That's that gizmo.
So it's polynomials with coefficients in ZP.
Mm-hmm. Laurent polynomials.
Laurent polynomials with one variable.
Yeah.
Okay.
Professor Richter, you had a slide saying something that if the group order was one of the TMF examples, saying that if the group order is invertible in the coefficient ring, then the Tate construction vanishes. Is this, is this something specific for TMF, or is it just true?
No, that direction is always true. if the group order is invertible in the coefficients, then your Tate spectral sequence collapses, and you just have one line. It's just trivial. So this direction is always true, but the converse, if it vanishes, the group order actually was invertible. That's usually not true. So that if and only if is sort of special in that case. But this implication, if the group order is invertible, Tate is trivial, that's always true.
Okay, thanks.
Any other questions?
I think there's another question in the chat.
Whether the question whether this is tame or wild, I mean, there's certain behavior that we wanted an explanation for. So, I mean, there are, for instance, certain descent results for algebraic K-theory, where you have very nice descent results in case of Galois extensions. And then there are other descent results that are weaker and more complicated to write down. And so it was sort of not clear how to relate this behavior to any sort of quality of the ring spectrum involved. This was one of the motivations. And the other one was actually what we saw so far in all these examples is just ramification at an ordinary prime. Well, in most of the cases, this was localized at a prime anyway, and then you saw torsion appearing at the only prime that could be torsion. So this is still very similar to algebra. What we actually expect as ramification at some other things, and maybe more types of ramification than just tame and wild, because in stable homotopy theory, there's one story at every prime, but then you have a filtration by some other things that behave very much like fields that you can use to localize. So so there's a filtration in stable homotopy theory by Morava K theories, and they live on a periodicity element. And what we actually hope to find is sort of ramification, where you see ramification at such a higher prime. And so this is, we were pretty sure that about the K-theory example, what to expect there. What we hoped was that you might actually see some other type of ramification. But with this method, this doesn't happen. But this could just say that this method isn't good enough to detect other types of ramification. So these were the main two motivations for actually trying that.
Thank you. He is asking, he's saying thank you and asking if there's any reference.
Yeah, that this is on the archive by now. Let me just, maybe I can copy the link. Just dump this in the. Oh. Wrong one. Ook. So that's a written up version is on the archive. So yeah.
Any more questions? So let's thank Birgit again. Thank you.
Thank you.
Thanks for the great talk.